Hello everyone, this is part 6 for important formula and concept for GATE 2023. Today we will discuss some important concept on fatigue. Fatigue failure occur when the metal is subjected to the cyclic stress. So there are different type of cyclic stress. These are some important terms related to the cyclic stress. Here I am plotting a one cyclic stress. Y-axis is sigma applied and the x-axis is the number of cycles to failure. This is one one cycle. The maximum value is correspond to this sigma max and the minimum stress is sigma min. The range of stress is defined as sigma r is the difference between a sigma max minus sigma min, and the alternating stress, which is also called the stress amplitude, which is defined by the half of the sigma r, which is the range of stress, and the mean stress is defined as sigma max plus sigma min by 2. And the stress ratio is the ratio between the sigma min upon sigma max, and amplitude ratio is defined as the ratio of alternating stress upon the mean stress. Now we will discuss the SN curve. SN curve is basically for a high cycle fatigue. High cycle fatigue, if the material sustain up to 10⁻⁷ cycle, we consider that fatigue is a high cycle fatigue regime. In the SN curve, y-axis is sigma A, which is alternating stress, and x-axis is the number of cycle, which is in log scale. For the ferrous material, we see a endurance limit. Endurance limit is the maximum stress below which the material can sustain infinite number of cycle. So this curve is correspond for the ferrous material, and for a non-ferrous material, we doesn't show any endurance limit. Material cannot show the endurance limit in non-ferrous material. This is non-ferrous. Now this is the Basquin equation. This determines the high cycle fatigue. So Basquin equation is a power law relationship which describes the linear relationship between the stress applied and the number of cycle. So just as per the SN curve, this is sigma and this number of cycle applied. So sigma amplitude, sigma A corresponds to the amplitude stress, and the Basquin equation is written as sigma A equals to sigma f prime 2n to the power b, where sigma A is a stress amplitude and sigma f prime is fatigue strength coefficient, and n is a number of cycle to failure, and the b is a fatigue strength exponent. So now we will move to the next topic. The Coffin-Manson equation. Coffin-Manson equation is used to define the low cycle fatigue, and usually the life less than 10⁻⁴ cycle is defined as a low cycle fatigue. Low cycle fatigue is usually occurs in the application where the load is generated by the thermal changes. So to quantify the low cycle fatigue, we use this equation, which is defined as sigma epsilon p by 2 equals to sigma f prime 2n to the power c, where sigma p is equals to the delta sigma fp is defined as the plastic strain amplitude. Epsilon f prime is a fatigue ductility coefficient, and 2n is same as the number of cycle to failure, and c is a fatigue ductility exponent. Now we define the Paris law, which is used to quantify the rate of crack propagation. Usually we plot a curve between dA upon dN versus delta K, where dA upon dN is a crack growth rate and delta K is the stress intensity factor, which is defined by delta K is equals to sigma max minus sigma min. In the Paris law, we have in the Paris equations, which is defined by dA by dN equal to C delta K to power m, where C and m is the material parameters. So this is a general crack propagation curve. Usually this is the non-crack propagation zone, which is called regime 1, and this is called the regime 2, where the stable crack propagation occurs, and this is the regime 3rd, where the unstable crack propagation happens. The next topic is minus rule. To define the cumulative fatigue damage when the material is subjected to a variable stress in service condition, we use minus rules. Which is defined as the summation of Ni upon capital Ni is equals to D, where small Ni is the number of applied cycles at a particular stress, and capital Ni is the fatigue life at that particular stress, and D, value of D is taken to as 1 when material fails. Now we will move to the LM parameters. So some component have a service life in years, which is not possible to perform at the lab scale. So to define the life at that much time, we use a LM parameters, which is defined as a P equals to capital T bracket ln T plus C, where C is a constant which usually uses 20, and T is the temperature which is in Kelvin, and T is the time taken in the hours. Now we will discuss two important creep failure mechanisms. First is NH creep. NH creep is most important at the lowest stress and the higher temperature. At higher temperature, the lattice diffusion is the dominant in the NH creep. The creep rate is directly proportional to the diffusion coefficient for self-diffusing through bulk the material, and the inverse relationship with the square of the grain size. The next is a Coble creep. Coble creep is dominant at the highest stress and the low temperature value, and in this creep the diffusion coefficient of the self diffusion along grain boundary, which means the grain boundary diffusion plays an important role in this creep, and the creep rate is directly proportional to the grain boundary diffusion coefficient and inversely proportional to the cube of the grain size. And due to the strong dependence of on the grain size, Coble creep is most important if the grains are small. Now another mechanism which plays an important role in the high temperature deformation, which is the grain boundary sliding. At high temperature, grains in the materials and ceramics move against each other, which means the grains have a higher strength as compared to the grain boundary. So grains start flowing across the grain boundary. So this mechanism is called grain boundary sliding, and the creep rate for this is directly proportional to the diffusion along grain boundary and the inversely proportional to the grain size. Thank you for watching the video. If you have any doubts, please type in the comment sections.